Right, hi y'all. I wanted to do a practice problem for amplifier circuit models from electronics. We're not exactly given so many practice problems. I know in the homeworks we've been given like A through J, then we give another second homework through it. And I will say that first problem, or the second problem where it makes it a large circuit, is pretty difficult. But I wanted to go over some here just in case anyone didn't understand. This was taken from, I think, 2007's Quiz 1. So just to go through it, the question here, or it says a trans reactance amplifier, which is this amplifier here. We can see it's a trans reactance one because we have a current dependent voltage source. And then we're also given this parallel resistor with a current known. So this signifies a trans resistance amplifier. Now the trans conductance one will have a voltage dependent current source. Usually it's denoted by G of M, or G sub M. Trans conductance usually will be denoted by that. And then we're also given this voltage across the terminals of this input resistance. Now, it doesn't have to be the input resistance because eventually we're going to have to find the input resistance. It could be, for example, if we can see up here, it could be something like this where the terminals of this are VI and we have some source resistance with an input resistance. This could be, again, the voltage across the or not the input resistance, but some two resistances, okay, sorry. There could be two resistances here after the source, because we could call that Vs. And this won't just be the input voltage, this will just be the voltage across this ith resistor. Of course, they could call that anything. So from here, what we have to do is we're trying to find the input resistance and the open circuit voltage gain. So what we're saying here is that AVO, the open circuit voltage gain, denoted by AVO, is in volts per volt. So we're comparing the input voltage to the output voltage. Essentially, we're saying how much times greater is the output voltage from our input voltage, so VO over VN. Or sometimes they say the output voltage over the source voltage. You'll see it either way, especially whenever you have this VN here at VI. Sometimes it won't be denoted like this, sometimes it'll say VS, but really we're just saying the input voltage or like a source voltage. So that's what we're finding. We're not even finding the output resistance, we're finding the input and we're finding the voltage gain. Now it's saying it's being put into this cascading form here. I'll scroll up here. It's put it into this cascading form. Cascading is whenever you put one after the other. You'll see this in op amps whenever they have cascading op amps. In this case, we're looking at cascading amplifiers. Now, the first thing I would do here is I would put it into this cascading form. I would connect these terminals F and Z to these terminals of B, F and Z. So let's do that now. Let me not try and let me try not to turn the page so much. Handwriting might be bad, but that's unfortunate. I'll try to make this as big as possible so y'all can see. Okay, so then this is here. Okay, and we can leave this like this, so that way we don't have to draw that other part. And then we'll say this goes here. Trying to make this easier for us to see. And we can then connect this here. Okay, and now this is again F and Z. This is our A. This is our trans resistance amplifier. Now we have to connect B to it. Okay, well B is, see, we have this line here. We have this resistance. Imagine that's a resistance and not some squiggles that I just put here. Again, now we have a plus and a minus VI2. And we have this weird, it looks like a feedback. If we can see up here, it looks like a feedback wire kind of. But then again, we have this ground voltage, or ground reference node, however we want to think about it. And then we have this voltage controlled current source, or voltage dependent current source. Again, we can put this as ground. This is going to be connected to this voltage current dependent source. Okay, this is also connected to ground. And then finally we have this plus. We have this minus connected to ground also, minus VO. Look how much smaller that got. My bad. Yes, my bad. So what we're trying to find is find this compared to this, V out over V in. Now let's get everything here drawn out here. RO2. I'm not going to put any numbers. I'm going to leave this as variables. But we know this here is on A, which is R, I believe that's 0, 1. And then, let's see. Yeah, I guess so. And then RI1, our output, I guess, yeah. RI1. And then we're also missing this dependent source here, which is RMII. And if y'all want to try this before I get into it, it would be very helpful for you especially. Say this is II, and then VI2 is here across what resistor? RI, is that a 3 or a 2? I'm going to assume it's a 2 because there's no 3. RI2. Okay. Now, we're trying to find VO over VI. Now, something I like to do is whenever I'm trying to find the gain, especially the open circuit voltage, either, it doesn't matter what it is, but I like to say, okay, V out over V in. Now, if you remember something from calculus, whenever you do the, what's it called? Your chain rule, especially in partials, whenever you do calculus 3, this can also be written as something depending on VI, which in this case it's II. I guess in this case it wouldn't actually work. Actually, it does, no. Oh, no. In this case it wouldn't work. So what I was trying to do was we would put something, we'll call this something X over VI times V out over X. That way the X's here will cancel and we're left with just V naught or V0 over VI. So most of the time it works because we've done a lot of them where it's just a transconductance where you have a voltage across here and then a voltage here, or of something of that nature. But that won't work in this case. What we're going to try and find is we're trying to find the current through this resistance because our dependent source depends on that current. So that's what we're going to be trying to do first. But before that, we can notice that the potential, the electric potential on this node here that I put this arrow on is plus V naught, or plus V out here. Now this can be traced here. This is the same node. This positive sign is the same as this positive sign. And now we can check the negative sign. The negative sign is connected to ground, which is just a wire that is in common with this point, and this point. So we can say the negative of VO is equal to the negative of VI2. In saying that, we know now that VO is equal to VI2. So we can replace Vout with Vi2, or we can replace Vi2 with Vout. What does that tell us for our gain? Well, that tells us that the gain, open circuit voltage gain, is also equal to Vi2 over Vi. I hope that makes sense. I hope y'all can see where I got the node from here. This positive point of this voltage is the same as this positive point, and the negative point, because it's connected to ground, is the same point negative here that is connected to ground. Now, we can solve for, I guess, some sort of open circuit voltage gain, or VO, using a node voltage if we wanted to. So what we can say is, let's see, Ri2 is here, Rout2 is here. So if we do node voltage, we would have to take this entire node. It would actually be pretty easy. I'll make a little dashed line here. This entire node to be, we'll say, node A. Then from here, what we can do is we can do node voltage method at A, and again, this is positive VO, which we can say is 0 is equal to VO over, and we'll start going to the left. So we have VO minus RM II divided by this resistance, R01, or Rout1. Now let's go here, there's no more, this is going straight down, okay, pretty good, plus, well again, we know this is Vout, I guess over Ri2, right? Vout over Ri2. Okay, so we have this one, we have this one. Now what about here, 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 okay, and we're leaving, okay, well this is just a current plus, because it's leaving, GM VI2. And VI2, we know, is VO, so we can rewrite this as GM VO. And finally we go to the right, and then we go down here. So then this is VO over Rout2. Terrible R. Anyways. Okay, so we have this equation, and we want to solve for some VO, because in our case here, we have all these VOs. This is what we want to solve for. VI we can find out, but it might be, let's see, there might be something with VI. In this case, there's not, but what is II? Okay, so what we're going to do here now, see if I can get that in the picture. Let's go back here, actually. II is what? II is VI divided by Ri1. This is the current going through Ri1. VI is the voltage across Ri1. We do a little bit of Ohm's law. We have II is equal to VI over Ri1. So let's write that down. That's pretty important. So we'll say II is equal to VI divided by Ri1. So rewriting this node voltage method equation, we can then say that 0 is equal to Vout, or Vout minus Rm times Vi over Ri1 divided by Rout1 plus Vout over Ri2. Get this in picture here, plus a GM Vout plus Vout over out 2. And this is equal to 0. I put 0 is equal, it doesn't matter, both sides. So we want V out over V in. Well, what can we do? Well, it kind of seems like, well, first of all here, let's try and get all the V outs on one side maybe, or we can maybe factor out a V out, however we want to do it. But what I might want to do first is, like I said, let's get V out on one side and V in maybe on the other. Okay, well, we know this has two terms. This has V out and V in. This only has V out, this only has V out, this only has V out. Perfect. But this has both. So let's split this fraction. We can say V out over R out 1 minus Rm Vm over, we have a fraction and a fraction, denominators, they come together. And I'll just bring this down, I don't want to rewrite it. But this is again equal to 0, so let's add Rm Vn over Ri1 R out 1 to both sides, of course. Now what we get here is this cancels, and then we have this VO is equal to VI. Of course, it has some resistances here. Now what we can do though is we can take out the VO. So again, let's drop down this these VO terms. Let's factor out VO. Well, what do we get? We get 1 over R out 1 plus 1 over R out, R in 2 plus GM plus 1 over R out 2. And I'm not plugging in any numbers. Remember, from the very beginning, we have these numbers. I'm going to try and just get an equation with letters. Just so what we can do at the end is we just plug everything in, we get an answer. We don't have to plug in numbers and then figure out, oh, do we have to multiply by this specific number to get this other variable? It's just too much work in my opinion. I think if you keep everything in terms of letters, it makes it very easy to solve and follow through your work. And of course, now this is equal to VI, parenthesis, we want to take out VI, Rm VI over, oh shit, that's not VI, we already took that out, R in 1, R out 1. So what do we want to do here? Well, we want to find the open circuit voltage gain, which is V out over V in. Wow, we have V out and we have V in. In terms of variables and values, we know. So that's very easy, just like I had said here. Now what we do is we divide by V in to both sides, and then we divide by this monstrosity. This is disgusting. What I would do first is I would get a common denominator, or just multiply. So what we can do is we can multiply, I think we can do this right, just to get rid of this denominator. But I think if you do anything to the left side, you have to do it to the right side, right? I'm gonna do what I know here. This might look a little bit ugly, I'm sorry. I'm just gonna divide everything here. So we have Rm over Ri1 R out 1 divided by, and then I'm going to divide by this whole thing, 1 over R out 1 plus 1 over R in 2. If you can do this, perfect, because this is going to take a little bit of time. R out 2. Now if we multiply everything here by R out 1 times R in 2 times R out 2, we have to do the same thing to the top now. R out 1 times R in 2 times R out 2. If y'all can see this, hopefully y'all are following this, because this is just algebra, but sometimes I get mixed up and I like to show all my work when I'm doing this. mostly because of exactly what's going to happen. You might get mixed up, and I might get mixed up here too. But we have this here, and now what we're going to do is we are going to, hopefully y'all can still see this if y'all are still writing it. I'm going to start doing the work on this next page to the right. So now what this is going to end up being equal to is we will get rid of all this denominator in the bottom, and actually here we can see R out 1 cancels with this one. There's no R in 1. Okay, no R in 1. We'll have to multiply by R in 1 on the top, but we know R out 1 cancels here, but it gets distributed everywhere else. That's what we have to be careful of. So I'm just going to write it here then. R out 1 gets canceled on the top, but R in 2 and R out 2 go to the top here. So what we have is Rm, R in 2, R out 2 divided by R in 1 divided by a total of R in 2, R out 2 plus R out 1, R out 2 plus GM R out 1, R in 2, R out 2 plus, what is this, R out 1, R in 2. So again, this looks kind of disgusting, and this looks very disgusting for sure. Do these have anything in common? Any of these? R out 2 maybe? No, they have nothing in common. Okay, well this works out pretty well. Hopefully y'all got that. Here we are with this work now. Let me get this flat now. Hopefully y'all caught that. Okay. So now we have this still complex variable or thing here. So now what we can do is we can multiply by R1 on both top and bottom. And now we just rewrite this as Rm, R1, R in 2. This is not an Rm. What am I talking? Isn't that a GM? What? I must be high. Oh, sorry. Where did I get Rm? Wait, Rm is there. What? Where's Rm? Oh my god, that's the dependent source. My bad. Oh, that's right. Okay. R1, Rn 2, R out 2 divided by, again, R1, R in 2, R out 2 plus R out 1, R out 2 plus GM R out 1, R in 2, R out 2 plus R out 1, R in 2, R1. And of course this is multiplied by R1 also, and this is also. Okay, but we can cancel out all the R1s. Can't we? Oh. This is supposed to be R in 1. Oh my god. Sleepy. Those are supposed to be R in 1s, and this is just supposed to cancel out. I don't know why I just left that there. R in 1 shouldn't even be here. That's the whole reason I did that, right? Okay. From here, I guess, I mean, you would be able to just plug it in. Now, I'm looking at the answer. I mean, it's going to give you the same answer. They just simplified greatly because they said Rin was, or Ri2 was very, very large. Which, I mean, fair. But we have Ri2 here, and we have Ri2 here, and here, and here. Well, we have it on top and bottom, so I mean, there's no real problem. It's just when you're plugging it in. Okay, that should be fine. Okay, let's see. I guess let's plug in values. Let's just see here. So this is gonna get ugly 100%. Let me turn on the light so I can actually see here. Okay, so Rm, y'all can see that. Rm is going to be what? 150? Oh, volts per milliamp though. I mean, I'm just gonna plug in everything face value. Ri2 isn't that 100 mega ohms? Oh my god. Oh my gosh, what the fuck? Well, that's 100 million. 100. So another 0. 100,000 million, yeah. Okay, maybe it was smart to put in numbers. Holy moly. Our out2 is 2.2. Oh wait, if I'm gonna do it in kilo ohms, I should 3. I should keep it to 100,000 kilo ohms. 2.2. I'm gonna keep everything in kilo ohms, and then because everything else is in milliamps, it should cancel out everything. R out 2 should be there, Rn2 is that, Rm is that value, and then it's divided by, this is where it's going to get ugly. We have Rn1, 200, so 0.2 kilo ohms, 0.2 times Rn2, oh my god, 100,000 times R out 2, 2.2, plus R out 1, 0.1, times R out 2 again. R out 2 is 2.2 times R in 1, 0.2, plus GM 40 times R out 1, 0.1 times R in 2, 100,000 times R out 2, 2.2 times R in 1, 0.2. Okay, it just has all of them. That's awesome. R out 1, 0.1 times R in 2, again 100,000 times R in 1, 0.2. Wow, okay, well, there we go. We got the answer here. 148.65 volts per volt. Okay, hopefully y'all can see that. This light is blocking it, kind of. 148.65 volts per volt. And now what we want is we want to do Rin. We want to find what is Rin. Rin is equal to what? So looking back here, what we would have to do is we would have to put a test source here and then find out what Rin actually is. Just looking at this though, what we can see is if we set this to be Rin and this to be R out, they show this notation in a lot of the quizzes and exams. Rin, they put an arrow showing in here into this V source, and then this V out, wherever you have V out is, and this arrow thing. So what you'd look at is, imagine you were the test source. What would you be seeing? Well, what you would be seeing in this case is this resistance, and you can't really see or feel any other resistance here. This is only, the current here is only affected by this resistor. That's kind of how I think about it. The test source will be applying this voltage across here, and this resistor will be drawing the current. Now, this current is only drawn out by this resistor. There's no other resistor connected in parallel. There's no capacitor or inductor affecting the current going through this resistor. If there was, however, for example in this one here, if we were to look here into this resistance, well, we have this wire here, this feedback kind of wire, that's connected to this, and it's in parallel if we want to see this. This node is the same thing as this node. This node at the bottom here is the same as this node. These two are in parallel. However, we're not looking at that here. This is not connected anywhere. There's no current flowing through this wire here. So Rin is essentially R or Ri1, which is 200 ohms. So Rin is equal to Ri1 is equal to 200 ohms. And that would be your answer for this, and actually this is the correct answer. and these two would get you the full points. So hopefully, this is really just a lot of algebra. I will say, whenever I was doing all these amplifier circuits on the homeworks, a lot of it was voltage dividers, 100%. You need to know how to do voltage dividers if you're going to be able to do this quickly. And whenever I was showing here this chain rule kind of thing, this is exactly what a voltage divider is. It's super easy when you know how to take that voltage divider. But connecting them in cascade, that makes it a little bit harder. But if you know how to analyze these specific circuits, it makes them very easy to use. Node voltage, especially here, use one node. If you want to use mesh current, go ahead. It's going to take a lot longer, a lot of equations. But here, this was one of the easier quizzes, 100%. I'll try and go over more. Hopefully this wasn't too much of a bore. The algebra was really kind of annoying whenever we have to deal with all these kinds of multiplications. But yes, thank you for joining.